other stuff. All right, to review where we have been before, we're talking mostly about this functional group, negative charge on a carbon next to a carbonyl, which has a resonance contributor. There's our hybrid. The combination of these suggested that carbon has nucleophilicity because it has negative charge, and as a matter of fact, that's what we're going to focus on today. Enolates are formed by deprotonating the hydrogen on the carbon next door to the carbonyl. We call it the alpha carbon and therefore the alpha hydrogen. And the different carbonyl containing functional groups are of different acidity, and depending upon what base we pick, we get a different amount of enolate formed. As we're going to see today, that's going to be an important issue. Whether there's a little bit or a lot of an enolate will control what happens to the enolate. So here in the case of acetone, we were talking about a ketone case, pKa typically 19. If we deprotonate it with hydroxide, the pKa of the conjugate acid of hydroxide, which is water, is 15.7. That tells us, based on the difference in pKs, that this equilibrium lies to the left by about 1,000. That means if I take acetone and react it with hydroxide at equilibrium, roughly only 1 in 1,000 of the acetones have been converted to the enolate. That enolate is swimming in a sea of acetone. That's an important issue. We'll get back to that later. The pKa, the acidity of the carbonyl compound, is a function of the stability of the conjugate base. The more stable the base is, the easier it is to form, the easier it is to take away the proton. So when the base is more stable, let's say in the case of this dione, more stable because there's more resonance contributors, it's easy to take the proton away. Sure enough, has a pKa of about 9. And by the way, you don't need to memorize pK values. pKa of 9, so that's a lot more acidic than acetone, and if we react it with methoxide, that's about equal basicity to hydroxide. The equilibrium constant in this case lies to the right by about 10 to the 6.5. That means roughly only 1 in something like 5 million of the diones have not been converted to the enolate when they're reacted with base. Now the situation is a little bit different with an ester, because the ester has this extra oxygen on it, and as we saw when we were discussing these resonance contributors, that oxygen works against the stabilization. The oxygen lone pairs are being contributed towards the area of the enolate where we're trying to spread out the electron density. So that is a destabilizing feature. It makes the conjugate base of an ester less stable compared to the ketone case, and consequently the ester is harder to deprotonate, higher pKa. So in this case, if we use methoxide and the ester, we only get about the equilibrium constant something like 10 to the minus 9.5, and that means somewhere between only 1 in 1 billion and 1 in 10 billion of the esters are actually in the enolate form. So if you do this, you have a whole bunch of ester and only a tiny, tiny amount of enolate. All right, so then we ask the question, which is especially relevant in the ester case. The base is also a good nucleophile, and do we have to worry about addition versus deprotonation? Carbonyls are subjected to nucleophilic attack from nucleophiles. Well, in this particular case, if you push the electrons, it's a moot point, because the substitution of this OCH3 for that OCH3 gives you the same thing. In other words, if I went like this and covered this up and drew on the overhead and came back, I could say, could you tell it it's been changed? Maybe you people sitting in the front who didn't see me pick up the pen would be able to say that, but no, we couldn't tell it was changed. In that case, it would be invisible. But if the base and the leaving group are different, then it can be an issue, as we talked about on the top of page 59. Imagine instead that you're using an ester in hydroxide. Hydroxide can either form the enolate or it can add to the carbonyl. Now, in analyzing this situation, we said maybe, since proton transfer is generally faster than nucleophile electrophile chemistry, then maybe all that's going to happen is an enolate is going to be formed. But number one, that's reversible. You can put the proton back on. And number two, only a tiny amount at equilibrium of the ester gets converted to the enolate. What was the equilibrium constant we saw on the previous page? 1 in a billion. So there's still, once the enolate has reached equilibrium, still plenty of ester left over to be available to undergo this nucleophilic attack, and ultimately this would lead to a carboxylic acid and a carboxylate. So if you want to do something with that ester enolate and keep an ester in your molecule in the end, this is bad. This is going to compete with it. How can we get around that? There's a number of ways to get around it, but it turns out probably one of the best is to take advantage of the fact that the hydrogens that we're trying to remove to make the enolate are generally less sterically hindered than the approach to the carbonyl. So the solution to that is to pick a base which is sterically hindered. And by making the base really sterically hindered, we, of course, we decrease the probability of attack on both of these things, but it becomes even worse at the carbonyl. So this sterically hindered base, there's a bunch of them, but lithium diisopropylamine, this guy, is the one that is frequently used, and we can see at the bottom of the page how that works. If we use LDA, here abbreviated as 2 isopropyls attached to the nitrogen, there's our base doing the deprotonation to make the enolate. None of the addition product is formed. An additional advantage to this is the fact that the LDA is a very strong base. Its conjugate acid diisopropylamine is a pK of 36. So the equilibrium, as it's written, has an equilibrium constant of 10 to the 11th. What that means is basically, if you'll pardon the pun, if I take 10 to the 11th, 100 billion esters, and put in LDA for all intents and purposes, they're all completely converted to the enolate. So you don't have to worry about any other issues. So that high equilibrium constant is useful as well. All right, now that brings us close to the point where we were last time, and that was the question on the top of page 60. The question was, okay, I made an enolate, big deal, what do I do with it? Well, an enolate has a negative charge. Whether you put the negative charge on the oxygen using one resonance contributor, or put the negative charge on the carbon using another resonance contributor, or even consider it from the viewpoint of the hybrid, in which the negative charge is shared by the oxygen and the carbon. All three of those structures suggest that this guy is going to be a nucleophile. And it turns out that is what enolates are really good for. Despite their resonance, enolates tend to be pretty good nucleophiles. But that brings up a question. Because there are two important resonance contributors, the carbanion 1, carbonanion 1, and the oxyanion 1, maybe we could form the new bond at two different places. If we use the carbonanion contributor, we make a new bond on the alpha carbon right there. If we use the oxyanionic contributor, we make a new bond to oxygen right there. This, by the way, is one of those reasons why when we see a structure that has resonance, we think about resonance, because different resonance contributors can lead to different products. Now, we might, on the surface, say, oh, okay, this is going to be the major pathway, reaction at the oxygen, because this is the major resonance contributor. Puts the negative charge on the oxygen compared to putting the negative charge on the carbon. The resonance hybrid has more delta minus on the oxygen than it has on the carbon. As it turns out, because of polarizability and hard-soft issues and things which we're not going to worry about here so much unless you'd like to worry about them. If you're a worrier, come and ask and I will tell you all about this. But we're not going to worry about exactly why it is. As it turns out, even though the majority of the negative charge is on oxygen, the enolate behaves like the majority of the charge is on carbon. In other words, for the reactions that we are going to see with enolates, the reaction is going to occur at carbon. Other reactions do occur at oxygen. We're just not going to see any of those. All right, so what kinds of things can we do? Well, enolates are carbon nucleophiles, as we've seen. And one thing that enolates are really, really, really good at is making new carbon-carbon bonds. As a matter of fact, that's the primary function that we use them for in organic synthesis, for making new molecules. It is one of the primary things that happens in biology when it comes to enolates and related molecules, like enols and enamines. These are frequently used for making new carbon-carbon bonds. So if we're going to make carbon-carbon bonds, we need to take the enolate, a carbon nucleophile, and react it with a carbon electrophile of some sort. And we've actually talked about two broad classes of carbon-based electrophiles in this course. The first ones were alkyl halides, like methyl iodide. In other words, we're just going to do SN2 reactions, where the enolate is the nucleophile and the alkyl halide's an electrophile. Here's an example of how we might do that. Let us suppose we have cyclohexanone, and we want to make a new carbon-carbon bond next door to the carbonyl with the methyl. Now, the first clue that this is an enolate reaction or something in that category is that the new bond is made on the carbon next door to the carbonyl. Many, but not all, reactions that make a bond there involve the stuff we're talking about, enolates, enols, or enamines. Now, we're adding So if it's an enolate, that's a nucleophile, so the methyl has to be an electrophile like CH3I. But the ketone by itself is not a nucleophile, or not much of a nucleophile. We convert it to the nucleophile by making the enolate, and that's what the base does. So our sequence is 1, put in base, 2, put in electrophile. So here's our mechanism. Base deprotonates to make the enolate. Now, despite what I just said about the enolate behaving like the negative charges on carbon, you will discover not only in the lecture supplement but throughout the Think book, I tend to use the oxyanionic resonance contributor for the enolate. And I'm doing that not to deliberately confuse you. I'm not that clever. If I wanted to deliberately confuse you, I'd find other ways to do it. I would obfuscate you by using what the Germans call, big words, right? What the Germans call Fachausdrücken, means technical terms. Unnecessary complication. But I'm not going to do that. The reason I'm doing that is because that is the best representation, if you have to use a single resonance contributor, that's the best representation for the enolate. It's like in many cases we use the best representation for a carbocation or whatever. All right, so now our enolate is a nucleophile. So there is the carbon-carbon bond formation. We take the pi electrons from the enolate. At the same time, the O- electrons come down. Does this look kind of similar to anything else we've done with an O-? Oxygen with a negative charge. Remember tetrahedral attic with a negative charge where the oxygen reformed the pi bond in a process of getting rid of electrons? That's a way to think about that. So we're going to take the O- extra electrons, reform the carbonyl, and you can think of it as pushing out, if you will, the carbon-carbon pi electrons to make the new carbon-carbon sigma bond, and then, of course, the leaving group leaves. It's an SN2 reaction in which the nucleophile is the enolate. And because it's an SN2 reaction, it follows all of the usual SN2 restrictions. For example, you have to have a good nucleophile, which enolates are. You have to have a reasonable leaving group. What do we know about iodide as a leaving group? It's a great leaving group. You have to have solvent, the appropriate solvent. That's not going to be an issue because we're not going to worry about solvent too much here with enolates. But generally, it's not too much of an issue with enolates. And the carbon that bears the leaving group cannot be tertiary. It's an SN2 reaction. Methyl, great, works beautifully. Primary, works pretty well. Secondary, okay. Tertiary, too sterically hindered. Here's an example of that. So on the bottom, imagine you had that same enolate except you reacted it with tertiary butyl iodide. So the carbon that bears the leaving group right there, tertiary carbon. Now, enolates, in addition to being good nucleophiles, are also kind of strong bases. What's the pK of where this guy came from? It's around 19. So it's a stronger base than hydroxide. And if it's too sterically hindered, instead of doing SN2, in fact, it does E2. So there's an elimination product. So this process, enolate alkylation, good for making new bonds to methyl, primary, even secondary carbons. Tertiary, though, out of luck, can't do it that way. There's actually other ways to do it, but we're not going to talk about them here. Now, we also talked about, more recently, using carbonyl compounds as electrophiles for making carbon-carbon bonds. We talked about adding cyanide. We talked about adding alkyne anions. We talked about adding Grignard reagents. Here we're going to talk about another nucleophile, enolates, reacting with carbonyl compounds. Now, like the other nucleophiles we've talked about and all the other carbonyl reactions, we can do addition or substitution. So let's start by talking about using enolates in addition reactions, which means we're going to take our enolate and react it with an aldehyde or a ketone. This process is called the aldol reaction. We'll explain why that is in a second. Now, here's an example of how that process might work. There's a ketone, there's an aldehyde, there's a base. And let's figure out what's going to happen here. Now, what are our reactants? Ketone, aldehyde, base, methanol. Methanol is not going to do anything. That's just the solvent. It's not strong enough to make, certainly not a strong enough of a base to make an enolate. So that leaves us with sodium hydroxide to make an enolate. Now, addition reactions can occur, but they're very reversible here. They're not going to move the mechanism forward. So what should we deprotonate? Well, we know that bases are good at making enolates, taking protons away from the carbon that's next door to the carbonyl. So that means I can deprotonate there. I can deprotonate there. Oh, by the way, conveniently enough, those are equivalent. Does not matter which of the 6 hydrogens of acetone I take away, I get to the same enolate. In the aldehyde, I can deprotonate nowhere. Here, remember, this is a benzene ring, and while the benzene ring has hydrogens, those hydrogens are not on the carbon that's directly next door to the carbonyl. We have an aldehyde hydrogen here that's directly bonded to the carbonyl, but it's not on the carbon next door to the carbonyl. So I can't take away that the aldehyde hydrogen to make an enolate. This particular enolate can't, or excuse me, this particular aldehyde can't form an enolate. So the first step in the mechanism, do the deprotonation, make the enolate. Now, what's an enolate going to do? Enolates are nucleophiles. It's cruising around the Friday night in the reaction singles bar going, I'm a nucleophile. I want to form a bond. Right? You can imagine it's got, how many of you watch what's it called, Jersey Shore? Anybody actually watch that? Nobody's hands go up, but you all know what I'm talking about, right? So you can imagine the enolate kind of cruising around going, hey, I'm a nucleophile, eh? Isn't that what they do in that show, right? And then what happens beyond that, they kind of have to put a black bar over the screen because you can't watch it. It's not HBO. All right, or is it HBO? I don't remember. I don't watch it, so I don't know. It's what? MTV? Oh, well, that explains it. Anyway, so it's an enolate. It's a nucleophile. What's it looking to react with? Electrophiles. What electrophiles are present? Aldehyde we haven't reacted with, but the ketone is also present. There's an awful lot of ketone present. Why do we know that? Remember I talked about the position of the carbonyl compound versus enolate equilibrium? This is why it's important. You've got to know how much carbonyl compound is left over when you've made the enolate, because the enolate could turn around and react with another molecule of what it came from. How much of this enolate is present? Well, let's see. Hydroxide and acetone, right? We saw that equilibrium. That equilibrium is actually on page 57, right here at the bottom. So there's our equilibrium. Acetone plus hydroxide, equilibrium constant 10 to the minus 3.3. In other words, when this comes to equilibrium, only 1 in 1,000 acetones have been converted to the enolate. This enolate that we've made here is swimming around in a sea of acetone. So it could react with more acetone. But the aldehyde is also present. In actually roughly equal amount, probably. So if you're an enolate and you're looking at a ketone to react with, and you're looking at an aldehyde to react with, which would you react with? Aldehyde, because aldehydes are more electrophilic. They are less sterically hindered, because here we've got this hydrogen instead of a methyl group, and they have a bigger delta plus on the carbonyl carbon because it only has one carbon group next door. So the aldehyde is more electrophilic. That's what the ketone enolate reacts with preferentially. So there is the reforming of the carbonyl. The carbon-carbon pi bonds of the enolate attack the carbonyl, and then because it's a usual carbonyl addition, the CO pi electrons become property of the oxygen. What does that give us? Hint. What does that give us? Yeah, tetrahedral adduct. How many times have we added a nucleophile to a carbonyl compound to make a tetrahedral adduct? Bree, are we up to like 100 billion gazillion, right? McDonald's, probably back in the days before you guys were born, used to actually keep track on their sign of how many billions were served. And there were bets as to when they were going to get to 100 billion because there wasn't room on the sign for 3 digits. So they solved that. When they got to 99 billion, now it just has billions and billions. So that's the number that's bigger than 99, and. Anyway, so how many times have we said a tetrahedral intermediate with a negative charge? Try to kick out a leaving group. What are our leaving group choices? Let's see here. Benzene ring? Never, ever, ever. Hydride. Does this look like that Chi-Chi-Bobbin reaction? No. So what's our other choice? Enolate. This is reversible. So the enolate, like a lot of other things, can leave. Now, It's irrelevant to this particular reaction other than the fact that this is in equilibrium, but it's relevant to us as human beings because if this didn't happen, if an enolate or if an O- couldn't kick out an enolate like that, we'd be dead. How many of you depend upon metabolism of glucose to live? Those of you who aren't putting up your hand, I guess you're clinically dead. For those of you who aren't putting up your hand, stay in your seat. I'm going to collect you after class and take you down to the med school. They pay $3 for cadavers down there. $3.50 if you've passed class. If you passed this class because you're worth more. The point is in metabolism of glucose, glycolysis. When you're taking apart glucose and making it into smaller molecules, there's a reaction that's very much related to this, in which an enolate is kicked out by essentially a tetrahedral adduct as part of that metabolism process. All right, anyways, those are not productive, so there's no leaving group to be ejected that's going to move the reaction forward. So what do we do then? Put a proton on, and there's our methanol. There's the product of this. So we've made a new carbon-carbon bond right there. It's an addition product because this used to be a carbonyl, and it's not now. This is called a beta-hydroxy ketone because the hydroxy group is on the alpha-beta carbon. Now, in the early days when people ran these reactions, these products were called aldols. Aldol is an abbreviation for aldehyde alcohol because the early version of this reaction was done with aldehydes instead of ketones. But the name stuck. So these products, these beta-hydroxy carbonyls, aldehydes or ketones that come from this kind of product are called aldols. Biology likes to do things like this. Now you might say, I've learned by now to ask the question when I get to the end, am I done? It's like when you're taking a long trip and you pull into your driveway at the end of the long trip, you still ask yourself, are we there yet? Am I done yet? Well, you might say, I've still got base present. Remember, everything's present at the same time, so even though you've gotten to this point in the reaction, there's still base floating around. As a matter of fact, you've just made more base in this step. You might say there's a proton next to the carbonyl, so could I take that away and make an enolate? Or in fact, could I take the proton away, form a pi bond, and kick out a leaving group at the same time to do an E2 kind of process? You might say, no, I probably can't do E2 here because hydroxide is not a leaving group unless it's being ejected from a tetrahedral intermediate. Now, we ejected hydroxide from a tetrahedral intermediate because two special things happened: charge delocalization and electron repulsion. So there were things happening in the transition state that lowered its energy and made it easier. As it turns out, you can do an E2 kind of elimination of hydroxide here, but there's some things that are special about it. Number one, it's conjugated. We have this little box down here. Number one, it's conjugated with a carbonyl. It's not just an issue of being conjugated. It turns out it's the presence of the carbonyl. It's the combination of the conjugation plus the extra acidity that the carbonyl gives, those two things together. So here's the second case where RO minus, HO minus, RO minus can leave. The first one was ejected from an oxyanic tetrahedral adduct. We see lots of cases of that. And then also when its elimination leads to, by strong base, take strong base, leads to conjugation with a carbonyl. All right, so overall here is the process. We took acetone, made the enolate, reacted it with the aldehyde to make the beta-hydroxy ketone, which then could undergo the E2 elimination to make the conjugated system. Now, the ease of this dehydration is a function of how much stabilization you get. The fact that this system has conjugation not only of the carbonyl with the alkene, but the alkene with the benzene ring, the added extra conjugation makes the dehydration, the elimination of hydroxide, even easier. In the laboratory, you may not even be able to isolate this. This dehydration may be so easy that as soon as this is made, it gets dehydrated. That's a laboratory issue. Sometimes you can stop it, sometimes you can't. We're not going to worry about it. We're going to assume that we have control and that we can stop here if we would like. Or we can go all the way to the end and do dehydration. Now, one last comment about that dehydration, because it's loss of water, we can do that under acid, catalyzed conditions as well. And I will leave that for you as an example to work out. Here we're taking cyclohexanone using formaldehyde as the electrophile. That's about the simplest carbonyl compound we can have. and then there's an acid step. You may be tempted to do the dehydration with base up here in part 1, but then why would the H2SO4 be present? So try to write that mechanism in a way that justifies why you need the H2SO4. All right, now we talked about up here using enolates for nucleophiles and carbonyl addition reactions. What about carbonyl substitution reactions? Well, we can do that. We can take an enolate, in this case derived from an ester, and do carbonyl substitution. Let's figure this out the same way we did in the previous case. Let's try to work out what the products would be. In this case, all we're doing is taking an ester, reacting it with sodium methoxide and methanol. And I do want to point out, bless you, I do want to point out a little quirk, a useful thing to observe in this reaction. The OR of the ester is the same as the OR of the base. If they aren't the same, then you might change what the ester is. So imagine you used an OCH3 methyl ester, but for the base you used hydroxide. It certainly might form some enolate, but it's also going to do that at substitution chemistry at the carbonyl, and then you won't have an ester anymore. So generally in these kind of cases, when we want to make an ester enolate, the base we pick, OR minus, is the same OR as we have in the ester. Now, let's predict what's going to happen here. Base plus ester, you can do the nucleophilic attack, but generally we look at the acid-base chemistry first, which would mean make the enolate. So here we make the enolate. Now, what's the enolate going to react with? Well, it could react with methanol and go back where it came from. That's not productive. Or it can react with another ester. Again, this ester, enolate, is only formed in a tiny amount, like 1 part in a billion. So it's swimming around in a world of ester. That's what it has to react with. That's what the electrophile is. So the ester enolate reacts with another molecule of ester. Carbonyl pi bond reforms. Carbon-carbon pi bond becomes the new carbon-carbon sigma bond. Pi bond goes away, just like every other nucleophilic attack on an ester that we've done, which takes us up to a tetrahedral atom with a negative charge on the oxygen. This is like 99 billion and 1. And what does it do first? Tries to kick out a leaving group. What are the leaving group choices? Methyl group? Never. Enolate? Sure, it can do that. It goes backwards. OCH3 minus? Yep. Remember the 2 circumstances. We now know 2 where RO minus or HO minus can be ejected. One of them is tetrahedral intermediate with a negative charge on the oxygen. Now you might say, why don't we protonate this? Remember that intramolecular gets considered before intermolecular. Feed the cats before we make coffee. This is feeding the cats. Remember that metaphor? How many of you have nightmares about that metaphor now? I hope not. I don't want my cats to be subject of your need for a psychiatrist. All right, anyway, so there's the ejecta leaving group. That takes us up to another carbonyl. We've done a carbonyl substitution, just like we've done so many other times. In this case, that's the piece that we've replaced the OCH3 with. And once again, we've learned to ask the am I done question. And the answer is no, we're not, because the proton that's on the alpha carbon between the 2 carbonyls, there's a hint, between 2 carbonyls. What happens to the acidity of a CH proton when it's between 2 carbonyls? Top of page 58. Right? Remember how easy it is to remove this proton here between the carbons, because we get this wonderful resonance stabilization. 3 resonance contributors, negative charge, shared over 3 atoms. So it's easy to take that proton away. Same thing happens here. Now, not as quite as easy as the diketone case, because this is a ketone and an ester, and esters aren't quite as good at making enolates as ketones because of that electron lone pair back donation we've talked about, but it's still another carbonyl. So this deprotonation occurs. We cannot avoid it. The equilibrium lies to the right by about somewhere between 10,000 and 100,000. 10 to the 4.5, that's about 3,000 or 4,000. Now, you might not want this to happen. Maybe you want to stop at the beta-keto ester, but you can't, because you can't wave your magic wand and say, Mother Nature, don't do that mechanism step. Do the other ones, but don't do that really fast, easy proton transfer mechanism step. So this is completely unavoidable. Now the reason I'm harping about that is because many times we don't want the enolate at the end. By the way, this enolate is stable enough. Most enolates are not stable enough you can put them in a bottle. This one, because it's delocalized over the 2 carbonyls, is. You could put this in the bottle like as a sodium salt if you really wanted to. But maybe this is the molecule that you want to stop at. So if you want to get rid of this problem, if you want to go back to here, you have to simply put in an acid to reverse the protonation. So what's our overall process then becomes do the base. That makes it up to this point. So these two together go up to this point, and then the H3O plus takes it back down to here. You have to put in the H3O plus if you want this guy back. You can't stop at this point. Now, this kind of reaction, first of all, is called the Claisen condensation because it's named after some guy, condensation. I'm glad you like that one. This guy condensation gets around, doesn't he, Bree? No, his name is Claisen. Now you're going to laugh. Okay. Claisen is the guy who basically developed this reaction. It's called a condensation reaction because what we're doing here is bringing 2 molecules together to make another molecule and ejecting a relatively small molecule in the process. Often it'll be like a small alcohol or water or maybe ammonia, something like that. Technically, when you bring amino acids together to make a protein, that's a condensation reaction. You're taking out a molecule of water. Usually, in a modern sense, the term condensation is referred to making carbon-carbon bond-forming processes. So this is a condensation kind of process. Again, Claisen condensation because it's a condensation reaction discovered by this guy named Claisen. There is an intramolecular version within the molecule. It's called the Dieckmann condensation, named again after this guy condensation. Right, that's his last name, condensation. There were 2 twin brothers, Claisen and Dieckmann. No? All right, anyways, Dieckmann. The Dieckmann condensation is just like the Claisen condensation, except it's intramolecular. It occurs within the molecule. Now, if you take 2 esters that are connected to each other by a carbon chain, and you take those 2 esters and bring them together to make a new carbon-carbon bond, what you've done is formed a ring, which is what the Dieckmann condensation does. So here's 2 esters, same sequence of reactants, base, followed by H3O plus. Right there is our new carbon-carbon bond. So this ester enolate substituted on that ester. Particularly useful reaction for making 5-membered and 6-membered rings. Bigger or smaller, not so good at doing that. But the mechanism is exactly the same, and I encourage you to go ahead and work it out and see how it gets there. Now, one of the questions you may have asked in this discussion of enolates is, I don't understand, how do I figure out what's going on here? In the enolate alkylation case, so enolate plus methyl iodide, I had the enolate, I had methyl iodide, I see that. In the aldol case, we had acetone, enolate, and benzaldehyde, I see that. But in the Claisen condensation, it was just 1 molecule. Why wasn't there something else? I don't understand. So what I want to talk about is how you identify what electrophile it is that's supposed to react with the enolate. Here's another example. If I take acetone, and in this case using barium hydroxide, it turns out that just is a standard way to do this exact reaction. You do an aldol condensation here, so it's the aldol reaction and a loss of water that makes this guy. This is an example of self-condensation. In other words, a molecule of acetone is reacting with another molecule of acetone. But if I take acetone and react with LDA and then benzyl bromide, phenyl CH2Br, we do that SN2 kind of process, we don't get self-condensation. We get reaction between these 2 guys. There's my new bond. You might say, how do I tell what's going to happen here? Well, there's a couple of clues to look at. Number 1, look at the nature of the base. Remember I was harping before on thinking what the equilibrium constant is, how much enolate is formed? This is where it becomes an issue. If you have a relatively weaker base, like hydroxide or methoxide, not very much of the carbonyl compound gets converted to an enolate. Maybe 1 in 1,000, maybe 1 in 1,000,000,000. But the enolate is swimming around in a sea of what it came from. Self-condensation is very common in those cases. On the other hand, if you use LDA, much, much, much stronger base. So strong that for all intents and purposes, it will take any of our carbonyl compounds and convert them completely to the enolate. And when the original carbonyl compound is completely consumed, then the enolate's swimming around going, hey, I got no carbonyl to react with, give me some other electrophile. So that's one thing. Also look for the electrophile. Now, a clue is in the way the reactions are written. This first reaction has no other electrophile other than the acetone that we start with written. In that case, it is our intention to use the starting carbonyl as the electrophile that the enolate reacts with. But if we write a second electrophile here, in this case the benzyl bromide, for SN2 reactions, that tells us that our intent is to take the enolate and react it with the second electrophile. Now, there are some laboratory issues with controlling that process as well. For our purposes, we're not going to worry about that. We're going to say, if I want the enolate to react with the second electrophile, I will write it the second electrophile and assume that self-condensation is not an issue. Again, there are ways to control that in the lab. Some of them are kind of tricky. They don't necessarily always work, but we're going to assume that we have control over that process. All right, so in general, if the base is RO-, self-condensation is possible, and it's very probable it happens frequently. If LDA is the base, self-condensation is usually avoided. RO-, not very much enolate. LDA, essentially 100% enolate. If the second electrophile is shown, then our intention is to react with the second electrophile. Otherwise, our intention is to do self-condensation. So that's at least how we can control it on paper. Again, in the laboratory, there can be real issues with it, but on paper, we're going to assume we have that control. Now, one last thing I want to say before we start talking about enols, and that is, when we talked about enolates, we really haven't talked about amides. And the reason we haven't talked about amides is not because you can't make an enolate from an amide. You can make an enolate from an amide. They're a little bit less acidic than esters, but you can make an enolate from an amide. But once you make an enolate from an amide, you can do alkylation of it, like SN2 kind of alkylation, but it won't do self-condensation. Remember, amides are resistant, pretty resistant to nucleophilic attack. It turns out enolates are just not powerful enough to add to amides. So most of the enolate chemistry you're going to see is on esters, aldehydes, and ketones. Occasionally on things that are more reactive, but usually not on amides. All right, now, let us shift to, on page 64, we're going to talk about enols. Enols are like enolates, except instead of having the C double bond O minus, they have the C double bond OH. We can think of them as kind of isomers of corresponding carbonyl compounds. In other words, if I shift a hydrogen over here and a pi bond over here, I have the carbonyl compound. We've talked about this before. Here's an example of it. Here is the enol, and here is the keto form. So conceptually, I've switched the hydrogen over here and the pi bond up here. These isomers are called tautomers. We've run across this before when we talked about hydration of alkynes. It shows up pretty frequently in biology. There's a lot of enols in biology. It was also important, actually, to Watson and Crick when they were putting together the structure of DNA. One of the key things they were doing near the end of that was trying to get the base pairs to line up. They knew that the bases were associated by hydrogen bonding. They knew how many hydrogen bonds there were. The problem was they couldn't get the geometry to work out right. And that was because for 2 of the 4 bases, they were using the wrong enols, the wrong tautomers. So when they told their machine shop to make them models that corresponded to the right tautomers, as soon as they put those into their DNA model, everything worked beautifully. Now, of the 2 tautomers, we're going to talk about 2 forms. The one that has the carbonyl in it, we call the keto form, not because it's limited to being a ketone. It's just the tautomer which has the carbonyl. Whether it's a ketone, aldehyde, acid chloride, ester, whatever, we call that the keto form. And if it has the double bond OH, we call that the enol. You can remember enol because it has en for alkene and ol for alcohol. If that helps you remember that. All right, so how does this interconversion work? Well, let's first talk about the position of the equilibrium since these guys are isomers. When there's nothing special to stabilize either side of the equilibrium, so take a very simple case like acetone. These equilibria favor the keto side, usually by fairly large equilibrium constants, in this case by about 1 million. And that is simply because the keto form is more stable than the enol form. If you take the bond energies of the keto form and add all those up, and the enol form and add all those up, what you discover is that the keto form is a little bit more stable by a couple of kilocalories. And stability, or equilibrium position, is about stability. But if you do something to stabilize the enol, then the equilibrium tends to shift a little bit more towards the enol. In this particular case, this pentane dione that we talked about before, its keto-enol equilibrium constant is pretty close to 1. It's not exactly 1 to 1. It might be 2 to 1 or 1 to 2, depending upon the solvent, the temperature, and so forth, but fairly close to 1 to 1, much closer to 1 to 1 than 1 million to 1. And so what is it that causes the enol to be more favored than the acetone enol? Well, it has two things. Number one, conjugation. In the enol form, we have 1, 2, 3, 4, 5 conjugated atoms, 2 carbons and 3 oxygens. The acetone enol has conjugation, but not nearly as much. There's 3 conjugated atoms in the acetone enol. So more extensive conjugation, we know what conjugation does, right? Gives the little kids more room to run around and go la 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 la. They have a bigger background or bigger backyard, they're happier. So here they have a bigger backyard. Number 2, there is an intramolecular hydrogen bond, the OH of the enol, hydrogen bonding with the other carbonyl, and that's completely absent in the acetone case. And hydrogen bonding, because it's an extra bond, is a stabilizing feature. Now, together or individually, those aren't worth much. Conjugation's worth a couple of kilocalories. The hydrogen bond's worth a couple of kilocalories, but the two together provide lots of stabilization and help favor the formation of the enol here. It doesn't disfavor the formation of the keto. It doesn't make the keto form any less stable, but it makes the enol more stable. Now, you can go to the extreme end of that and have phenol, benzene ring with an OH. That's a phenol with an OH. The whole molecule is called phenol. And this equilibrium constant is really, really, really large. I don't know off the top of my head what it is, but whatever 20 kilocalories or 30 kilocalories is, stuck in the equilibrium constant equation, it's really, really big. Here it's not an issue of well, it is partly an issue of conjugation, but it's not a hydrogen bonding issue. What is it that phenol has that the keto form doesn't have? Aromaticity. And aromaticity is worth lots of kilocalories. In the case of benzene, about 36 kilocalories. So even though we might not really think of this as an enol, we think of this as an aromatic molecule, it's still an OH next to carbon-carbon pi electron. All right, so now that we know about the position of the equilibrium, how do these guys interconvert? How does, for example, acetone keto form become enol form? There are 3 common methods by which enols will routinely show up. One of them is acid catalyzed, another one's base, and the third is decarboxylation. So acid catalyzed tautomerization, by far the most important of these, and it starts with taking our carbonyl compound in the presence of strong acid. What do carbonyl compounds do when they're strong acid? Protonate the carbonyl. How many times have we seen this? Here's a protonated carbonyl. Now think about what we're trying to get. You might say, okay, I can do that by taking a proton away. I can even think of it as taking the carbocation resonance contributor of this oxoneamine. Granted, not the most important, not the most significant resonance contributor, but maybe it will help you see where this comes from. One fate of a carbocation is BD protonated form of pi bond. So that's what this is. So this is moving the proton from the CH, putting it on the oxygen. We can't do that directly because that's a 1-3 shift. 1-3 shifts are forbidden. Achtung. Forbidden. Verboten. With all apologies to the Germans who are watching, my accent isn't that good. Not allowed. Can't do it. So if you have to move a hydrogen around, but you can't do it all at once, what do you use? You use the proton bus. That's what the water is doing here. Drops off the proton, picks up the proton. So proton bus kind of thing. You can also do the same kind of thing with base catalyzed tautomerization, because bases can move protons around as well, except because it's a base, it doesn't start by protonating, it starts by deprotonating. Make the enolate. There's an enolate resonance contributor, and if we put the hydrogen on the oxygen instead of the carbon, if we put the hydrogen on the oxygen, then we get an enol, and we regenerate our hydroxide. So this is base catalyzed. The acid, the one up above is acid catalyzed. We regenerate the acid at the end. Now, between the two of these, acid catalyzed, much more frequent. You won't see base catalyzed keto-enol tautomerization in too many circumstances, because once you've made the enolate, and there's usually not going to be very much in the presence of that carbonyl compound, what do you think happens? Aldol reaction. So not terribly important. A third way that enols show up occasionally is by decarboxylation. That's the loss of a carboxyl group. In this case, is a molecule of carbon dioxide. And this happens when you have a carboxylic acid, one carbon removed from a carbonyl. So it is a beta, in this case, keto acid. It can be any carbonyl, though. It doesn't have to be a ketone. It can be an aldehyde. It can be an ester, whatever. But it's got to be a carboxylic acid on the other side. So it starts with an intramolecular hydrogen bond. There's the carboxylic acid OH beginning to protonate, hydrogen bonding with the carbonyl. And because we have now 6 atoms in a cyclic arrangement, as it turns out, the electrons can shift around in a clockwise or counterclockwise direction. Here they're shown in a clockwise direction. So we form a new OH bond, break the carboxylic acid OH, form a new carbonyl, break the carbon-carbon bond, and make a new carbon-carbon pi bond all at once. So that gives us an enol and a molecule of carbon dioxide. This happens in some biological processes. It's a way of shortening a chain length by 1 carbon. Now, one last thing about this. Some people look at this structure and go, oh, I see what that looks like. 6 atoms in a ring, 6 electrons moving around. What does that look like? It looks like a benzene ring. But it's not aromatic. Unfortunately, some textbooks say this, and it's wrong. They say, oh, this is easy to do because it's got an aromatic transition state. It doesn't. Remember, to be aromatic, you have to have 6 p orbitals in a closed loop. The hydrogen does not have a p orbital. This is not a closed loop of p orbitals. It is, I think it's the arrangement of the atoms that's caused by the hydrogen bonding that gets everything started, but it's not aromatic. All right, next time we will finish up our discussion by talking about what to do with enols. We'll also talk about enamines, and then to the time that we have left over next week, we'll start talking about pharmaceuticals. See you on Monday.